So my name is Igor Minar. I'm a software engineer at Google in California, and I lead the engineering team that works on Angular. I came here to share some information about things we discovered as we were working on making things smaller, making things faster, specifically when it comes to tree shaking and dead code elimination, which are two optimization techniques we commonly rely on. But if you start talking about these techniques, we quickly realize that nobody really understands the whole thing end to end, and there are lots of surprises once you have the big picture in your head and you see how complex the system is and how easy it is to make mistakes. So let's dive in. Everybody says that applications should be fast, right? Anybody's building slow applications intentionally? Hopefully not. But let's define what fast means and how do we measure it. The most reliable way to do it is to focus on the critical rendering path and the time to interactive. Time to interactive is the time it takes for application to render something useful and become responsive to user input. Optimized application renders the most important part at the beginning as soon as possible, and then slowly loads more and more functionality, makes that available to the user. An optimized application loads everything up front and then provides all the functionality at much later point in time to the user. So how do we achieve fast? Tree shaking, right? At least that's what I'm being told, because everybody, when we start discussing this, everybody's like, oh, just use tree shaking, it's going to be fine. OK, so let's see how it works. Let's build an application. And we're going to build a very simple application, which is going to use vanilla JavaScript so that we have as little few dependencies as possible so that we can focus on the things that matter. I'm going to bring RxJS. Anybody knows RxJS here? Quite a few people. Yeah, we want the application to be reactive, to be fast, so RxJS comes in. And then we bring Webpack because tree shaking, right? Webpack does tree shaking, so we need the tree shaking, we put it in. It's going to be awesome. Before I go any further, I'm not trying to bash anybody. I'm going to show some stuff that is not pretty. My goal is to point out how this stuff works today and what we are doing to fix it. So if I picked any other solution, I would find problems. This is just a combo that I put together to demonstrate the problems. So here it is, my application. Ta-da! No applause? OK. Much better, much better. So my application is a stock dashboard. It just displays a few stocks, gets some data from stock exchange, and displays it. It's all fake. It doesn't really do anything useful. But it's a good explanation and good application to explore how this stuff works. So the architecture of the application is super simple. I just have few JavaScript modules. I have the index.js file, which brings in the view layer that I hand-coded and the data layer and bootstraps the application. The view rendering layer, it's just a bunch of string concatenation and inner HTML. Don't judge me. I was trying to make it as small as possible. And then the data layer, we use observables to create a stream of data that we're fetching from the stock exchange. The stock exchange is all in memory. Everything's fake, so it's super tiny. And we're using RxJS to use a few operators from RxJS to do all of this, to create the stream. It's really just a fraction of RxJS. OK, awesome. The application is really small. Just 125 lines of code with white space and comments, and like 3.7 kilobytes, unoptimized, just raw source code. Super tiny. It should load in the browser in a fraction of a second, right? Because it's reactive and tree shaken. So let's put it on web page test. This is slow motion. So we see in 1 second, there's nothing on the screen still. We're making connection. This is on a 3G device, low-end device. After 2 seconds, we have loading, because a static HTML arrived and displayed loading. And in about 3.8 seconds, we have something useful on the screen. So it really took 3.8 seconds to render application that has 3.7 kilobytes of source code. That's really bizarre. Let's take a look at what happened. So this is the waterfall chart that shows us how the time was spent to render this application. And what we see right away is that about half of the time was spent waiting for the network, and about the other half was spent downloading, evaluating JavaScript, and rendering the UI. So the first half There is not really much we can do about it except for using service worker, which is useful for return visitors. But for the initial visitors that even need to install the service worker, this is what they will pay. This is hosted on Firebase, which is super optimized. It has like all the tricks, HTTP2. It's really hard to do much better than this. So we can really only optimize the application by focusing on the second half. So we see that there's a lot of JavaScript activity happening. Let's check why. Well, there's 220 kilobytes of JavaScript in this application. That's really weird. How did that happen? We have several tools at our disposal to analyze what is being shipped, what is being loaded by the browser. I'm using two in this presentation, a Webpack Bundle Analyzer and Source Map Explorer. They both target the same JS file, but they show slightly different perspectives on what is present in the bundle. These slides and everything is going to be shared with you, so you don't need to worry about missing anything. Let's just focus on what is happening on the screen. Webpack Bundle Analyzer shows us the internal structure of the bundle as Webpack generated it. So it contains boundaries that Webpack generated to isolate modules, while the Source Map Explorer contains just the mapping of the raw ranges in the bundle to the original source code. And as we optimize Webpack and the internal bundle architecture or the structure, we'll see how these two views diverge in a significant way. OK, so 220 kilobytes. We see there is a lot of RxJS. We should do something about it. But let's start by going through the process of creating a bundle. What does it take to build a bundle? So first, we have our application source code. The application source code often references some third-party libraries. The application source code, if it's not built in a JavaScript that is runnable in the browser today, we need to transpile it. For that, we use things like Babel, TypeScript, Elm compiler, anything similar to that. This will produce application JavaScript modules, which then run in the browser. And we need to take these and link them against the third-party modules, against the libraries that we're using. For this, we use typically Webpack or Rollup. I'm using Webpack because I need code splitting, and Rollup doesn't do it. So Webpack is really the only option if you're doing code splitting that you can use today. This will produce a bundle. So bundle is a single file or multiple files, depending on your configuration, whether you're doing chunking or code splitting. And this bundle is not minified. It didn't go through any kind of like JavaScript code optimization. So we need to run it through minifier, whether it's an Uglify, closure compiler, or there are still other options. You get a minified bundle. And this is what we ship to the client. OK, so now we see that we have all these pieces. It looks slightly complicated. We talked about two optimizations, tree shaking and dead code elimination. Tree shaking, as we refer to it in the web community, often refers to what's happening in the bundle. And dead code elimination is what is happening in the minification phase. OK, great. So let's look at what is happening in Webpack. So tree shaking in Webpack is really live code inclusion that is happening at the module level. The granularity is module level. This is how Webpack 3 works. This might happen in the future version of Webpack, but this is how Webpack works today. The downside of this is that it will over-include stuff, because even if you have an import to a file that is not used, Webpack will bring it in. If you have a module from which you're using just one function, but the module contains 20 functions, Webpack will bring all the 20 functions. Not very good, but this is why we have the second stage of optimization. So let's take a look. For Webpack, we define an entry point that points to a module, and then Webpack starts traversing this module graph and finds that module A is needed because it's the entry point. Then we'll go to B. B refers to C, D, and we'll find out that E and F is not used, so it will not bring it, and it will create the bundle just from these modules. Great. So once we have the bundle created, that's when the dead code elimination comes in. This is what is happening in Uglify. This is code from my sample application that I built. Just a bunch of functions. What Uglify does, it analyzes the code, finds entry points using code analysis. It finds nodes in the AST that have side effect, and then traces everything from those entry points and finds what is alive, what is not. So in this case, we have a Webpack export. It's a property assignment For Webpack, for Uglify, that means that it must be retained for this application to work. So everything that is retained from here must be in the application. So we see that this assignment reference is a datafeed4 function. So we need to take that, mark it as needed. Datafeed4 also references a retry function, which is defined somewhere else. We mark that as needed. And Webpack sees that take until is not used by anybody else, so it can remove it. Great. So let's go back to application, and let's inspect the code to see why do we have so much of it. We're going to be looking for expensive imports. There are different ways to do this. I still go back and forth about what is the most efficient one. The tooling really sucks. So you have to have a little bit of luck, a little bit of knowing what to look for. But good one is visualizing the dependencies. Sometimes it can be too noisy, and it's not going to show you much, but it's a good one to try. The other one is just picking a symbol that you know should not be in the final application, and then tracing it back and seeing what are the retainers, and then from there you see what the problem is. So by doing this, through a lot of frustration, we find this import. In stock exchange.js, we're importing observable from the module RxJS. If you know anything about RxJS, you know that this is the way to get observable that is fully featured. It has all the operators monkey patched on the prototype, so you get all of the operators out of the box. Super convenient when you're debugging, when you're developing an application, because everything is right there, so you can just write the code like I did. Interval, start with map, every chain and everything. Beautiful. Auto-completion works in IDE. Nice. But then we end up with 220K. So it's not good. What can we do about it? There are two ways. Originally, when RxJS 5 came out, the solution to this problem was using this side effect, imports with side effect, through which you can bring operators as you need them. This has several challenges. If you change the code, you will not, there's no association between the operator and the code that uses it. So if you refactor the code, it's very easy to leave unused imports in, or change the code and break it because you've removed the side effect-free imports and the code no longer works in runtime. So in RxJS 5.5, we replaced this with a different way of doing it. RxJS 5.5 released just last week, and it has a lot of cool features. So this is one of them. What it allows us to do is to use these lettable operators. It's a much more modular way of doing using RxJS. And using this, we can only bring things that we need. So instead of bringing the whole RxJS or doing the unreliable side effect, non-side effect free imports, we can use this proper imports, bring in what we need, use it. Great. If we do this, we just shaved off 71 kilobytes from our application. Awesome. There is still a lot of work to be done, but this is a good start. So the recommendation from this is use modular APIs. Don't use monolithic APIs. Often, if you look at Lodash, if you look at RxJS, many other libraries, now they're starting to offer more and more modular APIs. Look for those and use them. Write linters or use linters that will catch any kind of usage of the old APIs that bring everything. So if you look at the bundles right now, we see that they're smaller, but there is still a lot of RxJS. And we're not using that much of RxJS. I really use just 3 operators in my application, so even if there are transitive dependencies, this is way too much. Unfortunately, the problem here is that we are pulling RxJS and also application in CommonJS format. This is something that is super difficult to find because nobody warns you about it. Even Webpack is very silent about it, unless you install several plugins that then gives you warnings. So in this case, I just knew, because I use RxJS quite a bit, that the path points to the CJS modules. CJS is problematic. We want to use ESM when we can. Why? ESM allows us to statically analyze code. Without evaluating code, we can find the imports and exports, find the shape of the module, and use optimizations to create smaller bundles, to tree-shake stuff, to just do better. The benefits come from being able to remove unused imports. We're able to concatenate modules, And we're also able to do code splitting, which is tricky if you're not using ES modules. Possible, but it gets really messy and it's error-prone. So how do we do it? In RxJS, it's opt-in right now because we need to be backwards compatible, so you have to create this alias. It's ugly, I hate it, but this is the only way how we were able to do it without breaking the world. In the next major version, this is going to be the default, so you will not need to think about it. If we do this, we shave off 3K. That's strange and a little sad. The reason for this is that for ESM optimizations to fully work, you need to have almost everything to be in ESM format. If you have even a small part of the application, especially the entry points, be in the common JS format, many of these optimizations will not work properly. So let's fix the second source of common JS modules, which is our application. By default, if you use Webpack Babel loader, it will downlevel the ESM imports to CommonJS. This is sad, but that's how it is. I wish the default was different, and I'm hoping that in the future you will not need to opt into this stuff. We should not need to opt in. If we opt in, we shave off 80K, because now all of our modules are ES modules, and Webpack can do more optimizations, remove stuff. So the recommendation is avoid CommonJS, avoid UMDs, because they're basically CommonJS in slightly different form, and do it from both your application and any kind of libraries that you're using. If you do need to pull in some third-party library that is in CommonJS format, try to do it in a lazy loaded chunk, because that will isolate the rest of the application. So now, if you look at the bundles, this is the previous structure, and this is the new one. We see that it's better. I'm not expecting you to read stuff. Just visually, if you see busy screen, that's bad. We want simple, big boxes. Okay, so we are reducing the number of modules in the bundle, but there's still a lot of stuff that remains. But we're making some progress. So, what are the other optimizations that we can do? I mentioned that ES modules is capable of module concatenation. What does that mean? We have two ES modules. We can analyze them, find the imports and exports, and then safely merge those two modules together to have just one module. We don't want to do this when we develop code, because we would just end up with one giant file that contains all of our code, and that would be a mess. But we want tools to do it safely so that we can write code in a modular way and then use tools to analyze everything, optimize stuff for us. With ESM, this is possible. But you have to opt in. It's not on by default. Okay, so we opt in. We use this plugin that is part of the core. It's just not on by default. And we shave off another 40K. So that's pretty good. We went from 220 kilobytes to 29. Usually through just opting into like the proper way of doing stuff. Okay, so if we compare the output from our analyzers, we see that it's significantly different. This is what we want, simple stuff, big boxes with big letters. What this means is that when the bundle is created, Webpack takes all of our code and merges them into a single closure that contains all of the symbols. And this is great for Uglify because it can analyze and find that code much easier. Without this optimization, Webpack often generates code for internal registry orchestration. It needs to create closures for each of the module and connect them together. And by generating this code, it often becomes the thing that prevents Uglify from removing the code that is not used by application, but just Webpack happened to generate code for it. So once you do turn on concatenation, Webpack does less of code generation in the bundle. Uglify can remove stuff, and stuff just drops. Great. So use module concatenation. This will reduce the module overhead and will improve the dead code elimination. So with all of these optimizations, when we look at how our application is performing now, we'll see that we can put the pixels on the screen in about 3.3 seconds. So that's time to interactive. Again, keep in mind that the first 2 seconds, that's the network. Not much we can do, so we are focusing on the second part. So we shaved off about half a second so far. We can do better. So the next optimization we can use is code splitting. Right now, our application is not showing anything until we have all the code present in the browser. So even though it's just 29K, there is a delay. Could we split the application so that we can render something useful and then lazy load the rest of the code? We can. In my application, the way I architected it is the view layer can actually be rendered separately from the rest of the application. This means that we can render the footer, the header, and basically the whole layout of the application without bringing any data. This is great. What does that mean? Is that in our current application, we just add a seam that allows us to split the graph into two chunks. In the main chunk that is used for rendering, and the second chunk that is just all the data layer and pulling data in. How does it look in the code? We look at the imports, we analyze the problematic one, which is the data import and the code that uses it, and we replace this with system import, which is the dynamic import. Soon this will be just import function, thanks to the new standard that was approved. Right now in Webpack, you have to use system import. Basically the same thing. Once we do this, we can analyze the bundles, and what we'll see is that we didn't shave off any code. Sometimes we add a few, 1 kilobyte or 2 kilobytes, because now we need to stitch the two bundles together. But what is important is that we now removed most of the code from the critical path. The main bundle is just 3 kilobytes large, while the data layer that we are lazily loading is 27 kilobytes. And if you look at the source map explorer that points just to the main bundle, we see that it's really just the code that we wrote and the operators that are necessary for our application. Great, this is what we want to see in the critical path. And when we look at the numbers, we see that we deferred 27 kilobytes. Okay, let's compare the user experience. So before we were at 3.3 seconds, now we can render something useful at 2.5 seconds. So we have the layout, we have some basic stuff, we don't have any data yet. At 3.5 seconds, we have data. Great, this is awesome. What sucks is that the data is rendered 0.2 seconds later than what it originally was. Why is that? Once you start code splitting, you're making a request, and this request, they create waterfall. So that means the application needs to render the initial screen and then realizes, oh, I need to go fetch the data. Let me fetch the code for data. And only then the request is made. What I can do about it, or we can do about it, is optimize the network through prefetch, preload, or HTTP push. In my case, because I'm on Firebase, I just use HTTP push. What this does is, when I make the request for my application, the server will send the index.html, and with that, we'll also send both the main and also the lazy data module, in that order, with those priorities. The end result is that we render the initial screen in 2.2 seconds, as opposed to 2.5, and the full screen in 2.6. So we improved both the full load, but also time to interactive, because the 2.2 application is interactive. So this is awesome. This is where we want to be. We now are adding just about 0.2 seconds on top of the network time. So if we have service worker, application will really bootstrap in just 0.2 seconds. If you look at what the waterfall diagram looks like, it's much more busier. We have several steps in there, and this is what we want to see. We want to see parallelization of requests, parallelization of work. So the recommendation number 4 is use code splitting, add seams to your application, but keep in mind the network latency issues and how that can bite you. So use it in combination with HTTP2 or preload, prefetch optimizations. So we talked a lot about the tree shaking, and let's take some time to look at dead code elimination. So as I explained before, dead code elimination is kind of similar to what Webpack does and what Webpack calls tree shaking. You can see how hesitant I am about these terms, because if you think about it, both tools do something very similar, just at a different level. Webpack does it at the module level, where it operates with the imports and exports. Uglify does something very similar, but it operates on AST, it operates on the symbols in our code. One thing to realize with dead code elimination, however, is that because it operates on AST, it has much harder time to statically analyze the application. The ES modules were designed to be statically analyzable. JavaScript has big limitations when it comes to static analyzability. So Uglify has to do much more, has to use heuristics, and has to keep things safe and often opt out and bail out of optimizations. What are the things that you should keep in mind when it comes to dead code elimination? Usually it comes to side-effected code in the top level of the module. So if you have your module, if you have a file, and if you, in that file you are executing a function or you have an IFI, then that's the thing that Uglify will consider as alive and not removable. Even if it doesn't have any side effects outside of that IFI, it will still be preserved. The most common way to down-level classes is using IFIs. So if you write any class, down-level it to ES5, you will end up with an IFI that Uglify cannot remove anymore. That sucks. The next thing besides IFIs is function calls, often used for function when you have a factory function that just initializes some state. Constructor calls, again, if you have just like var new logger in your application and nobody uses the logger, it will be preserved. And the last one is property assignment, which is the problem for Webpack, because Webpack uses property assignment all over to stitch internal module structures together. The good news is that Uglify can take some hints. And this was added recently, a couple of months ago. They added support for pure annotations, through which you can mark code that otherwise would be considered as unsafe to remove, and Uglify now can remove it. So what we did is we went actually through the whole RxJS and marked all the code that we know has no side effects. Most of our code doesn't have side effects, so it's safe to do it. Good examples of that is we have this retry subscriber, which was a class, was down-leveled, retained by Uglify. If we mark it with pure, it will be removed if not used by anybody else. The same with observable. This is a good example of a getter or factory function that is retained, usually without the pure annotation, new constructor call, and so on. So what would happen if we stripped all of these annotations and built the application? I wrote this shell command to just experiment with this. It turns out we will add 86 kilobytes back into a bundle. So after all of these optimizations we did, if we strip these annotations that already ship in RxJS and you get them out of the box today if you use RxJS 5.5, if we remove the annotations, you will be getting extra 86K. Not fun. So is it safe to use this pure annotation everywhere? Not quite. If it was, Uglify wouldn't need hints. It really comes down to best practices. If you write code that doesn't have non-local side effects, it's safe to do it. This is what we usually do. And sometimes, if you're breaking this rule, it's really just like when you're writing polyfills, or polyfills is probably the most common example. If you have code that has a global registry that you put stuff into as the code is being loaded, that's when the code is not safe, because you would just be removing stuff that might be needed. So be careful about where you put these pure annotations. The good news is that while today Uglify takes these hints, in the future version of Webpack, Webpack 4, will accept package level hint called side effects false, side effect free, or I'm not sure what the property name is because it changes. There will be a way to mark a package in the package.json as free of side effects, and that will allow to do similar optimizations in the Webpack level during tree shaking. So you might be thinking, this is insanity, right? Like, who should know all this stuff? And how do we discover this? How do we prevent regressions? Well, the only recommendation I have right now is you should measure and you should monitor. You should know what the application is performing as today. You should have a budget and know whether they're meeting the budget or not. And you should continuously monitor the performance of your application. This is the best we can do today. As we are improving the defaults and making it harder for you to not opt in, or you would have to opt out, you will have to think about this less and less. But right now, really just measure and monitor. So let's look at the final effect of optimizations. Before, we were loading the useful bits on the screen at 3.8 seconds. So TTI is 3.8. And after all these optimizations, we got it down to 2.2 seconds with the data arriving at 2.6 seconds. This is much, much better. Again, with Service Worker, you can shave it down to 0.2 and 0.6. So summary of the recommendations: use modularized APIs. Use ES modules throughout. I wish somebody would write a plugin that would make it more obvious when you're not doing it. This is something that you can help with. Turn on module concatenation. There should be a warning if you're not doing it, but it's not the case today. Use code splitting to defer code that you don't need for the rendering of the initial screen. And the last one is, if you have code that Uglify cannot remove because it might contain side effects, and you know that it doesn't, use the hints to tell Uglify that it can be removed. This is more of a recommendation for library authors, but if you think about it, everybody here is a library author if you build big enough application, because you have shared code, and that's where this problem becomes visible. And the last one is measure and monitor, because without that, you will be frustrated through regressions. You will fix things just to have more regressions tomorrow, and you will not even know about it. And usually, as you iterate, as you continuously change your application, if you identify the size of regression early on, it's much easier to know why it happened and fix it. If you just test the size of the application once a month, you made so many changes, it's really hard to you, but basically starting from scratch. So yes, all of this is messed up. It shouldn't be this way. But that's how it is, and we have to deal with it. It's improving. My team, the Angular team, is working with other teams to make sure that these things become default, so you don't have to think about it. If you use CLI, in the CLI, many of these optimizations, Angular CLI, many of these optimizations come turned on by default. And I believe that if we work together, we can make the switch over to the better path faster. So if you can help, please help. Thank you. I'm leaving the slides here.
Igor, thank you very much. Thank you very much for the talk.